Let me just start by reminding you that at least some version of the notes with typos and such is available online. So okay, so the first thing I want to say is something I did not mention last time, and I'm barely going to mention this time, is the diffeomorphism invariance of psi-DOs. So you can do this either in a local setting. So if you have Rn, and then you have open sets inside them, so like O and some U. And then you have a map, F between them. I don't know which way I want it to go, so let's say like this. And suppose you have a pseudodifferential operator, A, so it doesn't really matter. I'm just going to make this right now have compact closure. So it doesn't really matter what I do. So let's just put this here. And then you can ask, and let's suppose that its Schwartz kernel is supported in U cross U. So it's supported here. So this in particular says that it will map compactly supported functions in U to compactly supported functions in U. And then you can ask what happens if you pull this operator back by F. So what you do really is you consider something like AF, which is F star A, F inverse star, if I have my inverses right. So you take a function on O, pull it back by F inverse, apply A, and then pull it back by F. So one of the basic things, which is actually quite easy to show, it's sort of a change of variables trick, that this indeed is also a pseudodifferential operator. So here, these are supposed to have, for now, compact closures. And this is F is a diffeomorphism. Now, if you are you care about what's happening at infinity, the analogous statement, so an Rn bar, what you would do is similar. You would take OU sitting in Rn bar, open. So this is not a compact space. So these are open sets in this compact space. And suppose you have a diffeomorphism, F. Again, is a diffeomorphism going the same way. And then you can ask the same sort of thing. And again, you have the same sort of result that if A is a psi-DO with the Schwartz kernel assumption, but now you can have this double order. This implies that the analogously defined AF is again in the same space. And not only that, you can in fact compute things like principal symbols and wavefront sets. And all they do is they do the only natural thing that they could possibly do, which is to say that you have to think of I think I said it briefly, but maybe didn't really write it down. You're really supposed to think of both. So the symbol was a function on Rn cross Rn. You're really supposed to think of it as the cotangent bundle of Rn. And then what you're really supposed to be doing is to pull back functions on the cotangent bundles. That's the way the symbol behaves. And then the wavefront set was a subset of T star Rn. So again, you just take inverse images under the natural pullback. Okay, so I'm not really going to say more about this, except that this lets you go at once to manifolds in the first case and manifolds with boundary in the second case in general. And so that's giving you. This is actually what giving you. Maybe I should say it's a word that. So this lets you go to manifolds. While saying one more thing, remember that I said that the Schwartz kernel of pseudodifferential operators are C infinity of the diagonal. So when you go to manifolds, what you basically want is that near the Schwartz kernel on our manifold M is really going to be a distribution M cross M. You want it to be C infinity away from the diagonal. And near the diagonal, you make a sort of psi-DO. You take a local coordinate chart and then model it in Rn. And then this diffeomorphism invariance says that it doesn't really matter what you do. So it's sort of well defined. So this gives psi DOs on manifold. So say compact. I mean, you don't really need this, but then I don't have to say, otherwise I might want to say one more thing. And so the analogous thing here is again, say compact manifold with boundary. And then this is, in fact, one way of getting at what Melrose calls the scattering pseudodifferential operators. So this is Melrose's scattering IDOs. But basically, I mean, this is really an invariant statement. What we're mostly interested in are actually local in terms of microlocal analysis, so it's not so important for what I want to do. OK, so getting back to where I was at the very end, we want to talk about propagation of singularities. And so the sad is that we understand elliptic operators pretty well at this point. So we want to think about what happens if P is not elliptic. So P is going to be a pseudodifferential operator. And and so little p is going to be its principal symbol. And for now, we'll really think about most of the interesting things happening, say, to not complicate things too much. We are, say, interested in what happens at finite points in the base, but so at infinity in the fiber. But we're going to change this whichever way we like. So anyway, the simplest thing that can happen here. So again, remember just to have a simpler picture. We really, let's just think about, in fact, the classical space. You don't quite need that, but things makes things a bit easier. So here the principal symbol, little p, is essentially, so this is equal to, let me write it like this, it's going to be like z to the power minus l, zeta to the power minus m, times some smooth function, let's call it p0, where p0 is now a smooth function of Rn bar cross Rn bar. I mean, really the restriction of such a thing, but let's not say that. So this is our setup. And then you can ask what happens if this is not elliptic, i.e. if it has zeros. So the simplest way, OK, so basically the thing that you get to decide first, whether you want to think of this p or p0 as real or complex valued. And you get sort of different, what happens is different in the two cases. So corresponding to wave propagation, we're really interested in the real principal symbols. So we assume that this p0, really p0 restricted to, which I should have written at the very beginning anyway, but I just cited this. Let's assume that this is real. So I'm just going to abuse notation, also denoted by p0. So this is real. OK, so let's assume that this is real. So then the best case scenario, this has a non-degenerate zero. So what does it say? What does this mean? So this says that, well, I could say either way. But anyway, so P, essentially what you want is P equal to 0 implies that dP is non-zero. And so this says that you have that the zero set, so this implies that the zero set, which is the characteristic set of P, is a smooth submanifold. Okay, so that's the starting point. And then now what we are interested in is the thing that gives us the propagation structure is the Hamilton flow. So the Hamilton vector field, which so as a vector field is given by dp d zeta j dd zj minus dp d zj d zeta j. This is the Hamilton vector field. And so this is tangent to the characteristic set, to this smooth manifold. And so this the characteristic set is foliated by integral curves of HP. So the picture is that here's my whole board is the characteristic set. I mean, I'm coming out to say where p is non-zero, and then I have all these integral curves. So these are the HP integral curves. Now, of course, it could be more exciting than what I drew. So these integral curves, I mean, HP could vanish at some points in the relevant sense. So actually, let me just say this right away in order to be more honest. So what you really care about, the way you should really think about this HP, is that up to a rescaling, you should really think of this HP is a vector field on Rm bar cross Rm bar, which is tangent to the boundary. So concretely, HP is in. So let me write it out like this. So it's going to be in z to the minus L, z to the plus L maybe, minus 1, z to the m minus 1 times this space. Okay, so basically, I mean, you can see what happens here. So let's just think about what's happening when we are, at some finite points in z, but thinking of zeta going to infinity. So what happens here is that this might as well just think of this p also, if you want, as a homogeneous degree m function in the zeta variables. Then you differentiate with respect to zeta. It's going to be homogeneous of degree m minus 1. And so that's what this is dealing with. So if I multiply by its inverse, it will be removing that. And then here, this is still degree m, but there's a d zeta j, which is the degree minus 1 part. So the product altogether is degree m minus 1. Okay? So, so this HP, in fact, is, so if you think of it as start, it's a vector field defined on the interior of this compact manifold with corners. But in fact, it's a smooth vector field up to the boundary of this manifold with corners, just tangent toward the boundaries. Yes? Yes.
So this has a corner.
Yes.
So you never really define what is the manifold structure.
Oh, so the manifold structure is that, I mean, this is really just
standard definition. So
yeah.
In this picture, this would be restriction to the square of function which are smooth.
Right. Exactly. And so, I mean, so manifold with corners just as locally you are modeled on products of half lines and whole lines. Right? So this is the picture. Right. So we have this vector field, and whatever it's doing, so it's some vector field, whatever it is, and it's tangent to all boundary faces, including to the corners. I mean, these corners really have codimension 2, but they're not zero-dimensional except in one dimension. So it really should be coming out of the board, and it should be still tangent to that. But it's getting a bit hard to draw. Okay, so in fact, this is the picture. Now, even though, so I mean, HP is given by the symplectic form from dP, but the symplectic form is the symplectic form, so it's just slightly interesting things. And so it can very well happen that dP is non-zero, but in the sense I care about, HP is 0. So namely, note that the restriction of I don't know why I should. Let me call this. Let me write it like this. Plus. Let's give it a name. I'm going to call it a bold H, and I'm sure I'm going to mess up the notation at some point. But for a moment, let me have a proper notation. So the restriction of this is a vector field tangent to the boundary, to the boundary faces may actually vanish, even if dP is non-zero. And so what this would correspond to, so the actual Hamilton vector field HP cannot, because omega is a non-degenerate bilinear form. So it gives you an isomorphism between the tangent and the cotangent spaces. But what can happen is that so from the homogeneous perspective, here's my zero section. Here's my zeta directions, and so what can happen is that my vector field, Hamilton vector field, can become tangent to the dilation orbit. So HP can become. So I want to get rid of these things. Yeah, I mean, what I really mean is that this is equal to this. So I just want to rewrite. I just want to factor out these growing things, and then the rest is the HP. So it's not really, this is just the renormalized Hamilton vector field. Sorry, I put an equation in the wrong place. so HP can become tangent to the R plus orbits, dilations. It's still a perfectly nice non-zero vector field. But what happens then, if you look at it from the perspective of discompactification, on the boundary of discompactification, it will actually vanish. Okay, so it can become tangent to the R plus orbit, and this will mean so say at the point, say at alpha. And what this means is that HP, this rescaled version, actually vanishes at sort of the corresponding point. So here's my picture. This is my point alpha. Here's my compactified picture. This is the point at infinity, this bracket alpha. Okay. So what we really want to do, I mean, the general idea is that you don't want to have non-compactness just for the sake of having non-compactness. I mean, you should have an extremely good reason to have a non-compact object. So we really want to think of compact object. The compact object is the boundary of this compactification. And so on this boundary, we get a perfectly nice dynamical system, perfectly nice vector field, which, however, can have zeros even if HP does not have zeros. Okay? So I mean, the actual structure here, if you really wanted to do it honestly, it would be in contact geometry, but it's just so much easier to work with symplectic geometry that I think everybody likes to think about this. Okay, so a more honest picture of what the characteristic set dynamics might look like under this assumption is that you would have things like this. You would have some sources and sinks for the flow, and the Hamilton flow connects this sort of renormalized Hamilton flow connects these. Now, of course, it could. This is in some ways the best possible scenario you could have, in which nothing goes completely crazy. Of course, another alternative, what you could have is something completely crazy, some sort of crazy chaotic dynamical system. So this is a good scenario, and this is something that we actually want to understand. So there are two parts to it. You want to understand places where the Hamilton flow is non-trivial, and you also want to understand things like sources and sinks. Yes? No, I mean, what it would be is really a context structure on the boundary. And then, so, right. And so I mean, here, right, there's some arbitrariness because I factored out these things. So you should really think about this as being defined up to, say, positive multiples. And so really the integral curve should be thought of as defined up to reparametrization, direction preserving, orientation preserving reparametrization. Okay, so all right, so that's the basic picture. And then given this, the theorem, which, I mean, the original version is Hermander, and then in this form it's stated by Melrose, but there isn't too much work to do given what Hermander has done. The theorem is that So under these assumptions on P, in terms of the non-degeneracy, what you have is that and so reality of the principal symbol, what you have is that the wavefront set of order Rs well, first of all, you have a microlocal elliptic regularity. So let me record that. Elliptic regularity is just the wavefront set of U is sitting inside the wavefront set of order, whatever the order is, union the characteristic set. So away from the characteristic set, we just have elliptic regularity. And in the characteristic set, and so this is the propagation of singularities, so the wavefront set of U is a union of, let me put it this way, maximally extended by characteristics. So this means just HP integral curves. Sorry. Well, in the characteristic set, where, of course, PU is nice. So this would be R. I'm sorry, I have my orders the other way around. So R comes before S in the alphabet, but for some reason, I decided to write them the opposite way around. So differential order first, and then calling it S. So Q. So let me interpret this. So what this really says is the following. So suppose that you have a point alpha, which is, I mean, I can put it either way, but let's say alpha is not in the wavefront set of order SR of U. And then what the conclusion is, then the HP integral curve through alpha, so within, of course, within the complement of the wavefront set of PU, so where PU is trivial. So for starters, let's just think that PU has no wavefront set. So PU is, say, 0. We're looking at the solution of the homogeneous equation, OK? So then this is forgotten, and it just says that in the characteristic set, we have a statement. OK, so within, but if you don't forget it, it will be within the complement of the wavefront set of this. Through alpha is disjoint also. So in other words, if I draw the picture again, so here are my integral curves. These are the HP integral curves. So if I have a point alpha here, and suppose I know that U is nice here in the sense that it's microlocally in HSR, then the conclusion is that U is nice everywhere. So U nice at alpha, and this implies U nice on gamma alpha. This is the integral curve gamma alpha. Okay, that's the Hermander's theorem. And so let me just say that, of course, this is a completely automatic statement. I mean, it has no content when HP actually vanishes at the point. So it's not saying anything. It's only interesting at points alpha where this HP alpha is non-zero. Because otherwise, it's just saying that, well, the integral curve at the point where HP vanishes is just that point. So that point is not in the wavefront set implies that that point is not in the wavefront set. It's a very nice and easy theorem to prove, but you don't get many points for that. So All right. So this is the propagation singularities theorem. And so to put it in a different way, the estimate version so, I mean, even if I put it this way, you might not like it because it says something about singularities. But, I mean, such a thing by the closed graph theorem automatically implies an estimate. Of course, you really prove the estimate, so it's a ridiculous way of proving it. You need to use the closed graph theorem. But anyway, the estimate version is implied by this. It's not any weaker than the estimate. The estimate version is something like this, that you can estimate u somewhere by so u elsewhere, so again, it's going to be like HSR, HSR, plus PU in between. Plus some horribly weak norm of u. So this is anything. So and here the assumptions, what you need is basically so that these terms are a priori controlled by the theorem. So what you need is that whenever you take any point in the wavefront set of B1, so if for all alpha in the wavefront set of B1, what you need is that, well, either it's in the elliptic set of P. So first of all, OK, let me just, to start with, let me just state that, of course, this B3, so the wavefront set of, so this was already required in the elliptic setting. B1 should be contained in the elliptic set of B3. So remember, the wavefront set is where the operator, the complement of the wavefront set is where the operator is trivial. So the wavefront set is where the operator is not completely trivial, while the elliptic set is where the operator is non-degenerate. So a typical thing to think about is that the wavefront set being something like the closure of the elliptic set. Okay, okay, so this gives you an estimate in the elliptic region. So and also if alpha is in the wavefront set of B1, intersection the characteristic set of P, then there's a bicharacteristic which is segment, so contained in here in the elliptic set of B3, which reaches here, LB2 in sort of finite time, at finite parameter value. I mean, this is sort of understood. So, okay, so that's basically the estimate version. So this says, again, as I drew the picture last time, the sort of thing it says is that you can, so here's a straightened version. What it says is that you can understand, so this would be something like B1. It's, I mean, so the interior, think of it as the elliptic set, and the whole thing is the wavefront set. And then you have some bigger B2. And then you have to be able to reach it while remaining in the elliptic set of B3. Okay, so that's a picture. So that's Hermander's theorem. And in fact, this picture almost sort of proves it once I say what this picture says. So I'm going to give you a very sketchy version of the proof. So the idea of the proof, so I want to explain where commutators come in and where HP comes in. So this is a positive commutator estimate. And so in fact, it's related to energy estimates that you heard about this morning. Maybe I will have a chance to point out how it's exactly related. But so the basic thing you will think about is something like this L2 pairing PU-AU minus AU-PU, where this A is going to be some pseudodifferential operator of some order that eventually we decide. And just to make our life easier, we're going to make A equals A star. And OK, so let's just compute this for now. This is the L2 inner product. So A is A star, so I can write it as APU APU U, and then minus PAU U. So this is supposed to be a pseudodifferential operator, and these pairings are supposed to make sense. So we might have to. Did I do it the wrong way? P star. Yes, thank you. Very good. So, and what this is, so I probably wanted to actually write it the other way around, because now I'm going to get minus the commutator of what I wanted. But anyway, it doesn't really make any difference. What this is minus AP. I mean, so plus AP, sorry, the way I have it, minus P star A U comma U, which is, let me have a, OK, so let me write it as the commutator of A with P. So that's AP minus PA plus P minus P star A applied to U, paired with U. So this is the commutator. So that's the supposed to be the important thing here. So this P has real principal symbol. So let me just write down the order. So this is a pseudo of order m plus m prime minus 1, because it's a commutator, L plus L prime minus 1. This P minus P star is in psi m minus 1, L minus 1. So this product is in the same space. OK. So maybe actually at this point I should make a remark right away that what would happen if P is non-scalar, but its principal symbol is real. I mean, it's a multiple of the identity, scalar and real. Scalar and real, then in fact the same computation will essentially go through. So this is when you talk about the system. Same argument goes through. And so you will see why. So in that case, what you would do is you would trivialize so you're talking about system. So I mean, if you're really working the way I was talking about an actual matrix, then that's sort of trivialization already. But if you had a vector bundle, you would trivialize it. And then you would choose scalar operators A. So A is honestly given by some scalar operator tensor, the identity matrix, and then the interesting effects would come from this P minus P star, which would not be scalar anymore. But what we're going to do in this proof of it is we're going to dominate it anyway. So it doesn't make any difference. All right, so it's just a comment aside. So we have two terms, and I'm saying that this is a positive commutator estimate, and I have another term which is the same size. So it doesn't look so good. I mean, why is this the main thing? So in fact, you are supposed to think of this as a trivial term in some sense, in that you can dominate it, in fact, by the commutator. So let me say something about that. OK, so in fact, what you arrange, so let me try to get I mean, there's an I and there's a sign. So altogether, it's a recipe for disaster, being consistent for anything. So what I'm going to, I mean, the overall sign doesn't matter in the basic case that I care about, but it starts mattering at some point. So anyway, so what I want to do is I want to write this commutator, plus the other term. So I multiplied it by I just for the sake of having an I around, but not quite. I mean, the thing is that say P is P star, this term is gone. This is a commutator of two symmetric operators, so it's going to be skew symmetric. So the I makes it back to symmetric. So what I want to arrange, so suppose we can arrange that. This is equal to something like B star B minus E plus F, where the point is that this B is, well, it's, whatever, M plus M prime minus 1 over 2, L plus L prime minus 1 over 2. E is just twice that. So those are the orders that we computed before. And then F is lower order in every possible sense. Okay, so suppose I can arrange something like this. So you read this as saying that this commutator, sort of quote commutator unquote, is essentially positive. So it's positive where E is trivial. So it's positive away from the say the wavefront set of E. So and then F is modulo something that's trivial. That's the way you read it. So if you have something like this, what this tells you, going back to this computation and putting in some i's at some points, what this tells you is that BU squared, then you get an estimate like this, that BU squared minus EUU plus FUU. I mean, this sign doesn't really matter here because I didn't say anything about E, but this is supposed to show that it's going to go the wrong way. Anyway, so this thing is less than or equal to something like something that's coming from there. So I don't know. So since I don't want to compute my i's, I'm just going to write down 2 AUPU, something like that. And so what this says, I'm going to put all these terms on the other side as well. So altogether, it says, it gives you an inequality like this. Okay, and so now the interpretation of this is that, so here you're supposed to think that, so PU is, say, 0. I mean, this is not going to be this is where the equation comes in. I mean, if you don't assume that the equation holds, you shouldn't get an estimate. So this is supposed to be very nice. So if the PDE holds, that's very nice. And if you have control where E is non-trivial, so if U is a priori controlled, on the wavefront set of E, so this F is supposed to be a low-order term, so it's a relatively, not completely trivial, but relatively negligible term. Then, sort of modulo low-order term, we control BU. So i.e. U in whatever the order of B was. So U in H M plus M prime minus 1 over 2, L plus L prime minus 1 over 2 on the elliptic set of B. B, yes. Okay, so that's the this is the reading of a positive commutator estimate. Or, I mean, so the positivity is now this. So if you have a picture like this, and so what this is basically supposed to correspond to is exactly this. So here B1 is playing the role of B, B2 is playing the role of E, and then B3 is playing something in the role of A. So, so that's the rough picture. So if you have something like this, then you control U on the elliptic set of B in terms of control on the wavefront set of E. Okay, so this says that you can propagate control. Okay, and so I wanted an SR estimate, so you're going to choose M prime and L prime, so that those values are equal to S and R. All right, so So fine. So of course, this actually can't really directly prove the theorem, because an estimate like this is going to be working when U is extremely nice, and you don't a priori know that all these pairings make sense. So what you really have to do is you have to run a regularization argument, but that's not going to really do very much. Not going to hurt you very much. In fact, the way I'm doing it right now, it doesn't hurt you at all. All right. So that's how the positivity helps. Now the question is, how do you actually arrange this? Maybe I should ask any questions about this part. No? So how do you actually arrange this? Well, the answer is that I think I can erase this. Maybe I should say an answer is. So they have different choices of what you do. So one easy way. Now, easy doesn't mean, by the way, good, because easy good when it works, but then if you try to run the argument in another setting, it's not going to work. So easy is not always good. But in this case, it's fine. So easy way to arrange this is the following. What we're going to do is locally straighten out HP. So what this means, i.e. introduce local coordinates. Sorry. Let's call them Q1. So I can do this even just within the boundary, but even I can do it in a neighborhood of the boundary. So let me write it like this. So where Q2n is a boundary defining function. And if you had a codimension 2 corner, you need 2 at the corner. So there's really nothing changes when you're at the corner in this setting. So you want to introduce local coordinates like this, such that in these coordinates, HP is just the derivative in the first coordinate. So this you can always locally arrange. So it's just straightening out the vector field. And you're using very strongly that this vector field is tangent to all the boundary hypersurfaces. That's why you can do this. So OK, you've done this. Then the picture is the following. So I'm not going to draw this Q2n, because that gets too much. So you get exactly this picture. But maybe I redraw it just to have another copy where I can write this on. So this is the Q1 direction. Maybe I can actually make this into an axis. And then I have a bunch of other variables, like my. So I'm just going to talk about this case. This is just a notational difference. So I'm going to write Q prime as all the other Qs. So I don't know. I can go either way. I can either add the Q to n or not. It doesn't really make too much difference. OK, so I'm going to write something like this. And then let's just include the Q to n and then. And I might as well arrange this so that local coordinates are centered at my favorite point, alpha. So here's my favorite point, alpha. So the vector field is like this. And then now we go back, and let's see what we have to do to arrange this. So star just amounts to the following. Notice that I have absolutely no condition on f. So star just amounts to a principal symbol statement. Why is that? So the principal symbol statement is that so what's the principal symbol of the left-hand side? Well, the principal symbol of the commutator is just the Hamilton vector field of one applied to the other. So it's in this case it's minus and it's 1 over I multiplied by I. So it's just minus HPA. And then plus the principal symbol of this. So let me give it a name. So let's call P minus P star over 2I. Let's call this, I don't know, P tilde. something like that. So this is like the sub-principal part of P, the imaginary part thereof, more precisely. And then I'm going to call little p tilde is the principal symbol. It's one order lower, right? A big P tilde. And then I have maybe 2 times or something like that. Doesn't really matter. 2 p tilde a. So that's the left-hand side. And the right-hand side is just b squared. If b is the principal symbol of b, and I'm going to make it real, so I can just write b squared minus e. Right, that's what I have to arrange. All right, so so we just have to arrange such a statement. And now this is really easy because this HP of A is just, HP is just a coordinate vector field. So what I'm going to do is I'm going to take A to be of a product form. So just take A that looks like a function, I don't know, let's call it chi1 of q1, and then some other function, I don't know, chi2 of all these other variables q prime. And then actually, I will really also want a weight. So I have to put in a q2n to some power. It's supposed to be of whatever order it's supposed to be. I forgot, like m prime or something. So we are in Rn cross Rm bar, right? So we are away from the corner, and this is supposed to be the defining function of fiber infinity. So it's supposed to be like zeta inverse, minus, since defining function. So it vanishes at infinity. So, Let me have 2 functions here of q1, just so that it's easier to say. I mean, it's of course fine, but maybe like psi of q1, something like this. Okay, so if you hit this with HP, it's going to be great, because you only get to differentiate this q1. So you just get, chi1 prime psi plus chi1 psi prime times everything else, so whatever the everything else was. Okay, and then, of course, I also have the other term, but let's ignore it for a moment. Let me comment about it later. So now what we're going to do is, in this picture, so here's my alpha. And what I'm going to want to do is to propagate estimates from some point on the backward bicharacteristic. So this is, q1 equals to some value sigma, which is negative, going to be negative for me. And what I want to do is I want to take my this function chi1 times psi to look like this, basically. So this is chi1 times psi. So it's supposed to have a derivative, which is, let's see, did I get my signs right? Yeah, so I want to make the derivative negative along the q1 direction. So I want to take a function like this. So it has a negative derivative except in a small region like this. And this is where my e is going to live. Okay, so it has a good sign. And then I simply arrange this by taking chi1 of I don't know, some variable t to be something like I'm going to take some epsilon small, and then it's going to be something like a e to the some power. This is supposed to be a digamma in my notes. So something like this divided by t minus, say, epsilon over 2, and then 0. So this is if t is less than epsilon over 2. This is if t is bigger than epsilon over 2. So this is just a standard. This is just a standard compactly supported. I mean, not compactly supported, but sort of finite support. I mean, non-trivially supported bump-like function. Yeah, so here t is less than epsilon over 2, so this is actually a negative quantity, so this is exponentially decaying. And I want to take a psi that that looks like my psi is just going to be like it's identically 1 here. It's just a sort of ramp function ramping up around sigma. And so when I do this, psi, I mean, these two have derivatives which have the opposite sign. So so I can't just win. I mean, I can't have 2 squares. That would be, you gain without paying anything. But so I'm going to have these 2 terms with opposite signs. And so this is going to be the b squared term, and this is going to be the e term. I mean, once you multiply the various things together. Okay, and now arrange that I have a square minus an e, and my e is supported where psi prime is supported, which is very near this sigma. Okay, so so in other words, what I've arranged. Okay, and I'm going to take chi2. I didn't say that, so chi2 has some bump function near 0. Okay, so altogether, what I arranged, I have sort of a thin strip. That's the thinness is arranged by chi2, and then I have this bump, which has the good sign for what I want, and then apart from some small neighborhood where I'm going to have a priori assumptions. Okay, and then the upshot is that if I plug this in, then we are exactly in the setting that if things are nice on the support of little e, so i.e. here, we're support of psi prime, then things are nice on wherever this little b is positive, so where chi1 prime is positive or negative, whatever sign it has. Okay. So that's modulo regularization argument. That's the proof, at least if p was p star. If p is not p star, we have this extra term. So let me just comment about that for 1 second. And then go on to the. So if p is not p star, then we also have a term, something like 2p tilde a, also shows up. And so what? I guess I did mess up one thing, right? So my HP here is the honest HP, so I really should have the extra weight, the q to the power, 2n to the power m minus 1 or something, but it doesn't make any difference. Anyway, so what happens? This also shows up. What happens if this? What happens if this shows up? So the main point is here you have an a. So a is just that. And so what you're supposed to notice is that this has a chi1, and this has a chi1 prime. And the basic principle is you can always make chi1 be dominated by chi1 prime. So just use this digamma I added there. So make it large to dominate the p tilde term by HP term. So this is a general principle that always the differentiated term, differentiated expression can be used to control the other. I mean, you can just compute this and see, but I mean, in general, it's sort of easy to see. All right. So so the upshot is that we have. So this makes this is why this sub-principal term is completely irrelevant. I mean, it could be very large, but I can make this even larger. So who cares? And so nothing changes even if you make it into a system. Then this is going to be some matrix, but again just going to dominate it. So in norm, so it's all fine. Questions? Yes. You could. I already arranged too many things. So right. So all right. So let me see. So the few other things I want to add. So here there's no direction of propagation. You can propagate your estimates forward or backward. So the fact that I had a b star b minus e rather than a minus b star b plus e was completely irrelevant. Either way, you get exactly the same statement. So I was propagating now my. So this is one of the funny things that you always have to sort out the directions. I was propagating my estimates forward, which when you translate into a wavefront set statement, this says. So what this says, if u is nice here, then u is nice here, is what I concluded. So the what this corresponds to is that if u is bad here, then u is bad here. So I'm propagating estimates forward, which corresponds to propagating wavefront set backwards. But I mean, it goes either way. However, if I try to run the same argument in a slightly modified setting, where the slightly modified setting means that I don't quite assume that P has real principal symbol, so that's actually so drastically modified. Let me just point this out. So related, so this is called complex absorption. And here signs enter. So here we look at an operator, something like P minus IQ. And you think of this, so this is the absorption. And for, so certainly P and Q have both real principal symbol. But now the sign of this principal symbol of Q will make a difference. I mean, in particular, it should have a sign. So let's see, let's go PQ. I'm going to make Q greater than or equal to 0. So when you have this, then you can just go through this sort of calculation and check if everything is OK. This implies that estimates, so maybe I should write it like this. So Q greater than or equal to 0 implies estimates can be propagated forward. So wavefront set backwards, while Q less than or equal to 0 is the opposite way. Of course, when Q is 0, then you can go either way, and everything is great. That's what we discussed. But when Q has a sign, only one of the two directions is fine. All right. So OK, so rather than starting right away on the on these sources and sinks, which I will do quite quickly, given what else I want to get to, let me say right away that this gives sort of the simplest non-elliptic Fredholm setup that you could have. So this gives a non-elliptic Fredholm setup. So namely, if I consider this such an operator P minus IQ, and what I want to have is a picture like this. So sort of what I had before. So these are going to be my HP integral curves. So here I think of Q as a tool. So P is the real operator. P is the honest operator I care about, and Q I'm adding because it's a tool. So this way it's analogous to. You should think about this sort of a thickened version of something like a Cauchy hypersurface. So Cauchy hypersurfaces are not natural. They're not given. I mean, they're not coming from the operator. You put it in. It's a completely similar thing. You put this in. So you have a lot of choice what you want. If you want to arrange it that has whatever nice features, you arrange it has whatever nice features. So anyway, the picture you want to arrange is that some region like this would be a region where Q is greater than or equal to 0. Q greater than or equal to 0, but here Q would be equal to 0. So notice that where Q is positive, the operator is actually elliptic. So did I say this? That I mean, they're the same order. I should clarify this. So where Q is positive, of course, the operator is elliptic. So in the interior of this Q greater than or equal to 0, the operator is elliptic. So the interior, of course, we should have Q positive. You of course have elliptic estimates at such points. Estimates microlocally. And then what propagation of singularities lets you do is to, so say, for example, you have, so this is my HP flow. What propagation of singularities lets you do, you have the a priori information in here that U is controlled by P minus IQU. So let me say U. IQU, microlocally. And then what propagation of singularities lets you do in this form is let you propagate this control into this region where Q is identically 0 and all the way to the region where Q is, becomes greater than or equal to 0. So the propagation of singularities, one can propagate control into where Q is equal to 0. And so what you need is that all the integral curves of HP in the characteristic set, so all the bicharacteristics, reach Q positive. So if all bicharacteristics, so bicharacteristics just mean integral curves of HP in the characteristic set. If all bicharacteristics reach Q positive in both the forward and backward direction, so bicharacteristics, let me emphasize, so of P in forward and backward direction, then we get Fredholm estimates with the loss of one derivative. So let me write this out. So concretely, the estimate you get an estimate like this. So the global estimate would be like U in HSR is less than some constant. And so now you don't have to make any assumptions. So you see the problem with this wave propagation is that this is of the kind that if you have control of U somewhere, then you have it somewhere else. Well, but how do you start? How do you get the control in the first place? So I mean, the usual formulation is by Cauchy problems, and then you say that you essentially controlling it in terms of the Cauchy data. So if you don't have Cauchy data, so this is one way of doing this. So what you get is U in HSR is controlled by P minus IQU in H S minus M plus 1, R minus L plus 1. So this is the loss of one derivative relative to elliptic estimates. And then plus some trivial term, minus a trillion something or other. So this is the trivial. Trivial term. So you have this for U, and you have a similar estimate for the adjoints. So for P star plus IQ star U. So P star plus IQ star. So the thing to notice is that when you adjointify, what happens at the principal symbol level is that the sign of Q switches. I mean, if I get essentially P plus IQ as the principal symbol. So what will happen is that you will be able to propagate estimates backwards along the Hamilton flow. So this uses backward propagation. This is why I want this forward and backward statement. Okay, so so you have a similar estimate for P star plus IQ star, and then I want to use it with the spaces that are sort of duals of these. So that's, I mean, the orders here didn't make any difference, so I can just do that. And then what this says is that, so this implies that, so let me write this down once. This implies that this operator P minus IQ going from a space X to a space Y, where my Y is just going to be this space. And my X is going to have to be slightly funny. So this is U in HSR. That's what I would really like. But unfortunately, my P minus IQ is order M comma L. It's not going to map into that. So I want to say such that P minus IQU is in Y. Okay, so that's my x. So the statement is this operator is Fredholm. So this x with the natural norm you put on it is actually a Hilbert space. Moreover, because I only lost one derivative, this space depends on PQ, but only via the principal symbol on little p, little q. And so, from a symplectic geometry point of view, what this would be is somehow a first order in the sense that I have one extra condition. It's not like an iterated to whatever high order. It's like a first order coisotropic space. That's what it would naturally amount to. So, so anyway, with the slightly funny spaces, well, one of them slightly funny, you have a perfectly nice Fredholm problem, just as if you had an elliptic operator. So it's just as good as an elliptic setup. So what I'm going to do after the break is I quickly go through another way of getting Fredholm problems, which is what doesn't have the unnatural ingredient of putting in, but very, very convenient ingredient of putting in complex absorption, namely exactly this sources and sinks for the Hamilton flow. And I'm going to use this, so that should be maybe like 15 minutes. And then I'm going to use this to talk about asymptotically hyperbolic and de Sitter spaces. Okay, so let's take a break. So actually, before I say the source sink part, let me just make one more comment. I knew that I forgot to say something. The something I forgot to say is what about if you look at variable order Sobolev spaces? Another variation on this. So what if you look at variable order Sobolev spaces? Well, so what happens is let me just write it here since just a remark. So if I have variable orders, then probably singularities is what it is. If something is say just we're talking about forget about infinity, HS somewhere, then it's going to be HS somewhere else. You cannot get that better than HS. So if I have a variable where S is constant, right? So if I have a variable order Sobolev space, I can't just improve the order, where I'm supposed to be propagating things to. So so what we can have is that if the order S, so say, and sort of similar thing with R, but let me not try that on, is such that its Hamilton derivative along this HP is less than or equal to 0. So the space is getting weaker as you go forward. Then we can propagate estimates forward. So maybe I erase this much. So that would say the singularity is backwards. While if HP S is greater than or equal to 0, it's the opposite way. Can propagate estimates backwards. And this is very easy to see. What happens is that the changes that in the proof is that we had this Q2 to some power. This power was is minus m prime, whereas m prime was somehow related to the order S that we wanted to have. So it's given in terms of that. So the thing is that this m prime now again is going to be given by S. So it's a function, so it's a variable. If you differentiate this, then you're going to get a term with a log Q2. And the problem is that this log Q2 is the biggest term everywhere inside. So there's no way you're going to be able to dominate that. So it has to have, so when HP Q2n, sorry, it was. So this m prime, let me emphasize, this m prime now depending on everything. It's Q1, Q2n. Well, Q2n is actually irrelevant, so Q2n minus 1. So when you differentiate this with respect to Q1, that's the only non-trivial thing, you're going to get a log Q2n term. And this log Q2n term is actually the biggest term inside. So what that says is that the derivative of m prime, or of m prime along Q1 has to have the correct sign. But if it has the correct sign, then everything goes well. So that's basically what, I mean, it's sort of something closely related to what Unterberger did in the, I think, circa 1970. Now you might ask, so why am I doing this? I mean, here I'm throwing away information. I'm saying that I had HS somewhere, and then where S is some fixed number, like H10 here, and later on I'm just going to have H5. So why am I'm throwing away information? This sounds very silly. But of course, I'm allowing then that my P minus IQ is in the corresponding space. So this P minus IQ is in a weaker and weaker space as I'm moving onwards. So this is still going to be a Fredholm problem. So you're not throwing away any information in spite of appearances. It's just as strong as the constant order version, because you really have to think of the forcing, this P minus IQ, as the main object. So this gives you just an optimal result. And the reason why I wanted to say this, apart from that one can do this, is because it's very useful once you get into the setting of sources and sinks that I'm going to do right now. Okay. Questions? Okay, so let's do sources and sinks. So the point with sources and sinks is that, so let's just leave this for a moment. Is that you lose this ability to dominate everything by this sort of cutoff function in Q1. So what I really want to think about is like bundles of, I mean, it's not isolated, but I'm just going to call them sources. Okay. So the setup here in the compactified setting is that, so here I have Rn, so let's just talk about the interior so I don't have to write quite so much, but the same sort of thing works otherwise too. So that's my board, and then what I want to have is I want to have a submanifold, so embedded submanifold. So this is infinity in the momentum variables, which is a source or sink in the normal direction for the HP flow. So my HP flow is going to look something like this. So this would be a sink, the way I drew it. Okay, so of course you never ever reach the actual L. Now one way to say this, let me try to get my signs, is that that I'm going to take so say L is given by a vanishing of a bunch of defining functions, so something like rho 1j equals 0, where j goes from, I don't know, 1 through k or something like that. So these are defining functions for L, I mean, in a sort of non-degenerate way and all that. And I'm just going to take the quadratic version which is going to be so what they want to call it, rho 1. It's going to be just the sum of the rho 1j squared. So this is now a quadratic defining function of L. So it vanishes quadratically, but non-degenerately so at L. Right? So it's a quadratic defining function. So these vanish simply and non-degenerately, but you have to take the whole collection, add up the squares, you get something vanishing quadratically, but non-degenerately at L. What we want is that this function rho 1 has its Hamilton derivative has a sign. So you want something like minus plus. For whatever reason, I have this minus plus. I mean, it could go either way. So anyway, I don't know why I have minus on top, but there it is. So this should be something like beta 1 times rho 1 plus sort of good things. So here this beta 1 is going to be positive. And then f2 is going to be non-negative. And then my f3 should vanish quadratically. I mean cubically, sorry. Everything vanishes quadratically. So sorry, this is applied to rho 1. So what I want is that this defining function, this quadratic defining function is such that, well, so if you hit it with HP, it should be sort of getting back itself, because this HP is sort of preserving out the HP flow. So it should be getting back what you had, maybe times some function, which is supposed to be positive, so up to an overall sign. And then you could have some, it doesn't hurt you, certainly if you allow some extra term, which is non-negative. And then this is sort of modulo cubically vanishing terms. So that's basically what you want. I mean, let me just say this. One way that this gets created, so example would be, example is if HP ML actually vanishes. So this is sort of actually the most important example, but unfortunately, this is, for example, true in something like a Schwarzschild, but it's not true in Kerr. So HP in the relevant place. So HPML vanishes. Vanishes at L. And so in this case, you're really thinking about the linearization of this dynamical system. And then this sort of statement is exactly a sort of a source sink statement in the honest sense. Okay, so vanishes at L, and the linearization has has some neutral directions along L. Along L, plus its and all other eigenvalues are well, like one case negative, the other case positive, I guess, whatever. So that's sort of an example to keep in mind, but this is sort of a more general version. So the more general version is needed for shows up in Kerr or Kerr de Sitter. Okay, so that's L. Now I think I can erase this. So what this says basically is that if I have a cutoff function in row 1, I take a bump function in row 1. So row 1 is non-negative, right? It's a sum of squares. If I take a bump function in it, so it's like 1 near 0, and then I cut it off, then if I cut it off close enough so that these cubic terms can be neglected, then I'm going to get a sign corresponding to this plus minus. So this means that cutoffs cutoffs in row 1 give a sign. So if sufficiently localized, so that F3 can be neglected, which you can certainly arrange. Okay, so that's the first bit. But so this is not going to give. So cutoff in row 1 is supposed to look like this. This is my row 1 axis. So remember, it's non-negative, and so this is some function like this, some chi. Let's go with chi2. All right. But so this is identically 1 or something, some constant here. So it's not going to give me. It gives a sign in an indefinite sense everywhere, but it's not giving me a definite sign near 0. At L, though. Okay, so how am I going to get? So what can give me any sign at L? So the only thing that can help me is so for example, let's think about this case. This HPML actually vanishes at L. So I mean vanishes. Then then how am I going to get a positive commutator? So you have to remember that what really shows up in the calculation, in this commutator calculation, is the Hamilton vector with HP, which has also a radial part, which we killed off by going to the boundary. So you really care about, so at L, what can give positivity is the is the radial part. So this is to say something like the in this local coordinates that I had, it's something like the Q2n, dd Q2n, that kind of thing, part of HP. Right, so I said this HP, when rescaled, is actually a smooth vector field up to the boundary, which is tangent to the boundary. So we are saying now that this vector field tangent to the boundary actually vanishes at L. So this means it vanishes as a vector field, as a smooth vector field. But it doesn't mean that it vanishes as a B vector field, so as a vector field tangent to the boundary. Namely, it can still be a non-zero multiple of this Q2n, dQ2n. This vanishes as a usual vector field, but it's non-trivial. And the reason why it's non-trivial, because we have a weight, right? We're going to apply this not to a smooth function of Q2n, but Q2n to some power. And when this thing differentiates that Q2n to some power, it's going to bring down that power, which can give us a sign. So the point is that this can give, so then the weight, which was this Q2n to the power minus m prime, do give a contribution to the commutator, to the principal symbol. Remember, it's no longer the case that the vector field is ddq1, so we can't arrange this anymore. So they do give a contribution to the principal symbol of the commutator. But what this means is that, and then what starts playing a role, and so this is the only thing that has a definite sign at L itself, but then what starts playing the role is the relative sign of these two contributions. So just so that I don't mess up my signs, let's have, I'm going to call rho 0, something like that. Yeah, okay, so rho 0 is going to be Q2n, just so that I have my consistent notation. And then what I want is that this is equal to the Hamilton derivative of this, rho 0. So this is just rescaled, but I mean, it's not restricted to the boundary right now, so I'm sure I will use my notation at some point now. It's a multiple of rho 0, where this beta 0 at this L is positive. So what this says, basically, so also assume. So what this says is that this L is not just a normal source or sink within the boundary, but also if you think of the boundary as just as well as the boundary of the bulk, and so as a total picture, the total picture is what's a good way to draw it? Here's going to be my L. So this is the boundary. And then the whole thing is Rn cross Rn bar. And so what I really want is that this is say a sink in this picture, also from the interior. That's what this sign is saying, so with some definiteness here. Okay. And so what will happen is that this is what shows up in scattering theory, and so Euclidean scattering theory, asymptotic Euclidean scattering theory. Same thing shows up in like de Sitter space or Kerr de Sitter space. So all these settings have exactly this geometry. So that's why this is an important example. But so with all this, there's one more thing now that we can't get rid of, which is the subprincipal symbol, I mean, this p minus p star term. So beforehand, we could beat it because we had this cutoff, and this cutoff could always make the derivative so much bigger than anything that's not differentiated. But here, the only thing that that we can play with is this q2n. And so, the same argument would say that if I make m prime large enough, then I can do whatever I want. But so so that means you're really changing the space in which you are working. So if you don't want to say that I'm just not going to work out what's happening, then you have to actually work out what's happening. And the p minus p star will contribute. So you can write it down explicitly. So just normalize it. So I'm going to normalize things so that where do I have my normalization? So I want to write my p tilde. Remember, this was the symbol of p minus p star over 2i. So I want this to be something like plus minus. So the minus is the top signs always match everywhere. Something like 2, beta 2, beta 0. Sorry, the wrong thing. I'm copying. I'm copying completely the wrong thing. Beta 0, beta tilde times, I don't know whether I rescaled it. If I didn't rescale it, I should add the row 0 to the power minus m plus 1. So this is just the order m minus 1. Okay, so it's just the q2n. I mean, it's just the zeta to the whatever power. So is equal to this. So beta 0, just that positive quantity that came in from here. And then so the beta tilde is really just defined by this. This is really the definition of beta tilde. Meaning what it really enters at the end of the day is sort of a re-normalized version of p tilde. Okay, so beta 0 is the sort of the normal to the boundary eigenvalue of this dynamical system. Okay, and so the offset is when you do this, is that you can, if you now write down a commutator calculation, so if you take a commutant, quote commutant, uncommutant A, which looks something like essentially, so you might want to modify something slightly, but let me just cheat. You want to write down something like this chi2, as I called it, of row 1. So it's going to be some cutoff in this. And then it's really going to be this row 0 to the power minus m prime. I guess that's what I had. So this is going to be our commutant. And am I missing something? I don't think I'm missing anything. So if I write down this A, just work out my positive commutator estimate, the upshot will be the following. So I really get two terms. So we get two terms. And then the relative sign. So this is the chi2 term versus this term. Relative sign depends on whether this m prime is above or below a threshold value. I mean, this threshold value really just comes from, there's another, I mean, you would say 0 just by staring at this, but there's this sub-principles in this beta 2 also as a contribution. So rather than writing this down, let me just say what the actual output is at the end of the day. So the output is that, if I find this, my numerology for this, well, okay. So the actual proposition in this case is there are two cases. So there's a high regularity. So this is when the regularity S, I'm going to ignore R. So I'm going to be away from one of the boundaries. I could put everything in, but then there's more notation. OK, so actually, let me start with the low regularity because it's, OK, I'm just leaving it like this. So the high regularity version is that I'm going to assume that S, my differential order, minus m minus 1 over 2 plus that beta tilde that I defined there, that this thing is positive on L. So this is my differential order. It's positive on L. And in fact, I already have another number, S prime, which satisfies the same inequality. So S here is supposed to be bigger than S prime. So the assumption here will be really that I'm going to prove HS regularity given HS prime regularity, where S prime is bigger than this threshold. The threshold is m minus 1 over 2 minus beta tilde. So m minus 1 over 2 minus beta tilde is the threshold regularity. Okay, so we're going to prove a regularity statement. And so here, okay, let me say it like this. So let me write it analogously to what I had for a propagation estimate. So then we have an estimate like this, B1U HS. So I'm going to completely drop the R's. So this is going to be less than a constant times, so I think it was B3 PU H S minus m plus 1. So the same numerology as I had before, nothing changes, plus UHMN. So then we have an estimate like this if U is a priori in this better space, HS prime, so let me put it this way, and BJR is in the picture that I'm about to draw, so that I don't have to say it. So again, this is all in these notes that are online. So I'm going to draw a picture in a second. While the low regularity result is now, I'm not going to assume something like this. So low regularity means that S minus m minus 1 over 2 plus beta tilde is negative on L. So S is low, it's negative regularity, I mean relative to this threshold. And then what you get is a propagation of singularities like statement. So I'm going to now still have a B2U. Well, I can get rid of the N, whatever. Some result like this. Okay, so the picture that I promised so here's the high regularity. Here's my L. And I want to estimate U nearby. So I want to have this B1. So I'm going to just take a, this is going to be my the wavefront set or elliptic set or whatever of B1. And then I just need to have a B3 that's a bit bigger. So that's B3. So what it's saying is that select control for free. Wait, did I say the? So of course I should, if U is in HS prime, microlocally at L, of course, only. So the assumption is at L itself, we have HS prime regularity. So just a tiny bit, anything just a tiny bit better than this threshold. Then for free, so it's not like propagation, for free, we get regularity in a neighborhood of L, provided that, of course, PU is nice in the neighborhood of L. So that's a control for free. So it's not like the propagation of singularities. But the low regularity picture, so this L is a source sink. So I mean, it's a sink if you go whichever direction, either forward or backwards. So here's my L. And then what I'm going to do is, again, I want to have regularity here. But it doesn't come for free. This is like propagation of singularities. I have to be able to control it sort of outside. So it's going to be my B2, sorry for the inconsistent color coding. And I should be able to propagate from B2 to B1 in the elliptic set of B3. So my integral curves are going like right? So the upshot is that you can propagate in the low regularity version if you know regularity here away in a punctured neighborhood of L. So away from L, you can propagate it up to L. Okay, I mean, this is, again, assuming that you can move from one to the other within the elliptic set of B3. And it's exactly the same numerology in terms of what shows up for PU as in the propagation of singularities. But in this case, you just get information for free. So it's like, what could be better than that? Okay, so maybe I should say, so an example of, so I could have add R's and really have the radial set go to the corner, but then just even more notation. So rather than doing that, let me say that the simplest example, maybe it's not the simplest, but the simplest example that is that people are widely interested in, example is Euclidean or asymptotic Euclidean scattering theory. Scattering theory. So in this case, you look at something like Laplacian minus some spectral parameter lambda. So lambda is, this is a positive Laplacian, as lambda is positive. So this looks like it's the principal symbol is now like zeta squared minus lambda. And so this is now in the full sense. So of course this is elliptic in the standard sense, but it's not elliptic at base infinity. Right? The characteristic set. So if it's P, characteristic set. So it's reversed now. I'm not at fiber infinity, at base infinity, but it doesn't really make any difference. The characteristic set of P is just the set of. If I want to write in a homogenized notation, but where this is now homogeneous. This is a homogeneous variable. Just like normally you think of zeta as homogeneous, I'm just interchanging them. I think of z as homogeneous. So it will be this, such that zeta squared is equal to lambda. And z is non-zero, I guess, if I really want it homogeneous. I mean, z is really at infinity. But in the homogeneous point of view, you just write down everything. So this is the characteristic set. And then what happens is that this has this is actually a radial set. Which is where zeta is proportional, z and zeta are proportional to each other. So I should say z is some constant times zeta, or proportional to zeta. Okay, so maybe there are two components. So one is, so let's call it, say, R or L plus, for would be, I mean, this is a slight abuse of notation, but okay, let me write it like this. So this would be like zeta hat comma zeta, such that zeta squared is equal to lambda, whereby zeta hat, I mean zeta over zeta, and I think of the unit sphere being at infinity just to normalize things, and then you have an L minus where I get the opposite sign. Okay, so this is my z, and this is the zeta variable. And then the way the Hamilton flow looks is just this. So the Hamilton flow is, so this is going to be a bit hard to draw. There are just too many dimensions. But the basic picture is the following. So what the characteristic set is really at each point at infinity. So you have a sphere at infinity. So the circle is the lowest interesting dimension you can imagine. So you have a circle at infinity, and over each point of the circles in each direction at infinity, you have a circle in the zeta variable. So you have a torus, really. And so here's my torus picture. So this is my z hat variable. So this is a circle, but I can't really connect it back. So the whole thing is a torus. So these are the zeta variables. And so I have on top, so this whole thing on top is my, well, I don't know, whichever way. Let's say this is the L minus. This is the L plus. And then let me get rid of these lines, because then the way the HP curves go is like this. And so there's a similar thing on the other side. So this is a torus, right? So there's another side to it. So this is the way the HP flow goes. So and these exactly are satisfy the hypothesis that I had here. And so now you can cook up very easily a Fredholm framework to analyze this. To have an operator that's honestly invertible, or at least almost invertible. What you want to do, you want to work with variable order Sobolev spaces. I mean, in this case, it's really the order is the decay. The variable, because we are at infinity, the variable part is just the decay. It's just the decay. And what you want to have is you want to have a space with a high regularity. So you get to choose which way you want to go. Say you want to go from L minus to L plus, then you want high regularity at L minus, and you want low regularity. So low and high are defined exactly in that way at L plus. So maybe I should point out that if P is P star, which would be the case here, then this beta tilde just goes away. And then your threshold is just the order of the operator minus 1 over 2. In this case, the order of the operator in the relevant sense, which is decay, is 0. So the threshold is minus a half. So the question is whether you're in a better weighted L2 space than the one with a sort of minus half order of decay, a half order of growth relative to L2. That's sort of the borderline space there. OK, and so if you set this up now, so that you have a sort of variable order Sobolev spaces, so the order can be constant near L plus minus, so you don't really have to prove this theorem I had for variable orders, but it doesn't make any difference. Anyway, so it could be just constant there, but it's supposed to change somewhere in between. So it starts being very high, and as you and as you go, it becomes low. I mean, it doesn't be very high; it has to be just above and below the threshold. Then you again get this propagation of the estimates. You also, when you dualize. Here you were in a low regularity space, I mean, so in terms of decay. But anyway, low regularity space, when you dualize, it's going to be a high regularity space, so you're going to be able to propagate it backwards. So this is exactly what you need for a Fredholm setup. So if you just define this x and y as I did, but now with this variable order Sobolev spaces, there is your Fredholm problem. And so this is, so in scattering theory, this will be one of the things that this would correspond to something like the limiting absorption principle. So that's what it looks like from this perspective. Any questions on this? As I said, there's a much sort of like a full detailed write-up. Yes?
This way you get all this version of the limiting absorption principle, also with this incoming and outgoing cutoffs and all this. Right, exactly. So it exactly corresponds to this incoming, and this change in the order corresponds to exactly this incoming, outgoing part, yes. All right, so to get to what we're really interested in these lectures, so eventually Lorentzian problems, let's just do that right now. So let's talk about de Sitter spaces and asymptotically hyperbolic spaces. So what will happen is that, I mean, this is sort of became some aspects of this are sort of clear from the lectures we had this morning. The general philosophy is that analysis on de Sitter spaces de Sitter spaces really only requires what we talked about now. So what have we talked about? This is microlocal ellipticity, real principle type propagation. So this is propagation of singularities and radial points. depending on what you want to do, technically at some point you can add complex absorption, but it's not crucial. So what happens if you go now to a space with a black hole? So the Kerr version. So the Kerr de Sitter, that is. So I'll talk about this to some extent tomorrow, but I think in the workshop at the end, Samuel Jatlo will talk about this in way more detail. One X-ray ingredient, which is this normally hyperbolic trapping. So I mean, you heard this morning hyperbolic trapping, that there's trapping in Kerr. So the same thing happens in Kerr de Sitter. So Kerr de Sitter is just sort of a cosmological constant background. Same thing happens in Kerr de Sitter. And as you heard, you really should be in phase space to understand what's happening. And I mean, at least using like Fourier modes or something. But you should really be, I mean, in the sort of microlocal analysis perspective, should be really in phase space, and it's this. This is the sort of extra part that we need. And so this is work of. I mean, it's a number of people. In fact, Christian Girard has worked on closely related things a while ago. But in this form, it's really the work of Samuel and Jatlov, who will probably talk about this. So I think I can ignore this a bit. So not say too much about it. So I want to explain this setup here. So what really happens? Now, so first of all, I should say, what is de Sitter space and what's hyperbolic space? Okay, so in Minkowski space, so let's just start with Rn plus 1. So this is Minkowski space. So in this, we can take the two hyperboloids. So we can take so let me just draw the picture. So this is a light cone. And within this, I can take the 1/2 of the two-sheeted hyperboloid. So this is going to be a hyperbolic space if I just restrict the metric. So it becomes Riemannian if I do this. And I also can take the one-sheeted hyperboloid and then restrict the metric. And this becomes de Sitter space, which is Lorentzian. So here it's again, there's another copy. There are two copies of hyperbolic space. Okay, so that's what they are. So you can just work out what they look like. But rather than doing this completely directly, let's just do it from the perspective of, I think, the very first lecture, which was we compactified, so radially, Rn plus 1. So now we have, I'm just going to do a 2D picture because, you know, it becomes hard to draw. So in the 2D picture, this is my Rn plus 1 bar. So these are this is the light cone going out to infinity. So these are all the null directions. They all go from this radial perspective. This is a geodesic compactification after all in a Riemannian sense. So all the null geodesics will go to this 45-degree angle sphere. That's I mean this temperate circle, whatever one might call it. Anyway, so here the hyperbolic space is like this. And the Sitter space is like this. Now, what we can do here is start with the wave operator. So G is Minkowski. And so I don't know to what extent I'm going to write things out, but my favorite signature is this. But I might not write things down sufficiently. It's clear. So the downside of this signature is that you get the negative of a Riemannian metric, but well, that's life. So start with the Minkowski wave operator, and then what you can do is again you think of this compactification being the fundamental thing. So the R plus action is what's driving you. What you can do is you can take a smooth transversal, which would be the unit sphere, say. So the n sphere. And then what you can do is you can conjugate this by the Mellin transform. So Mellin transform along r plus orbit. So the dilation orbits. And so the upshot is that you get the family of operators on the sphere, so Mellin transform box, and get the family of operators ups on the sphere. Okay, so that's all fine. So differential operators with smooth coefficients. There's absolutely nothing singular that's happening here. The wave operator had no singularities. This thing is not going to have any singularities. But now we're going to do something crazy, which is, however, useful. Something crazy is that, well, if we ran this argument with the Laplacian rather than the Euclidean Laplacian rather than with box, what we would have gotten as the transform is essentially the spectral family of the Laplacian on the sphere. So essentially the same calculation tells you if you do a slightly different Mellin transform, which you can do either in the interior or in the exterior of the light cone, but which becomes singular at the light cone. So if you do a sort of a metric, so Minkowski, so therefore bad in the smooth structure. So this is, remember, smooth structure is much more important than a metric. So this is a bad thing to do, but nonetheless, it's going to relate to the objects we care about. So you do the metric Mellin transform. So this is to say, i.e., Mellin transform relative to the hyperboloids. Now, what do I mean by this relative to? So what do you use in the Mellin transform? The Mellin transform is an integral. The Mellin transform looks like this. Mellin transform of u is, so I call it something like xy, is an integral x to the minus I sigma, blah, 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 dx over x. So what you get to choose, this is the choice. What is my x? Okay, I can make different choices. So here, when I use this, I use a function whose homogeneous degree 1 function, or degree -1, depending on what I want to do. Anyway, I use a function which is 1 on the sphere. And that's the nice thing to do, because it's a smooth transversal, smooth non-linear transversal. It's a great thing. Here, I do something crazy but useful, which is I use a function which is 1 on the hyperboloids. So I use x, which is 1 on hyperboloid. So it's like it's the Minkowski distance function, essentially, up to like sines and whatnot. Now, if you do this, then exactly the same calculation, I mean, it's just in a Lorentzian signature, but that makes no difference. It's an algebraic calculation. The same calculation as for the Laplacian gives you that the Mellin transform, maybe up to a sine, because this was, remember, it's a negative of the Riemannian metric, so it's a bit of a nuisance. We get the spectral family of the Laplacian on hyperbolic space and the wave operator on de Sitter space. So that is to say, this minus constant. So this constant is going to be something like n minus 1 over 2 squared plus sigma squared, where sigma is the Mellin dual parameter. Now, how are these two things related to each other? So this is the good thing, this from the smooth structure point of view. So this is love. This is the bad thing from the smooth structure point of view, but it gives you something that relates to two objects you care about. So how do they relate? Well, if you just stare at what you're doing, so the relationship of the two transforms, of the two Mellin transforms, is essentially, I'm saying essentially just because of one small thing, which is that you have to remember the wave operator is not homogeneous of degree 0 with respect to dilations. So you have to sort of re-normalize it by a homogeneous degree 2 function. So it's essentially conjugation by the I sigma power of the ratio of the two functions we used to do the Mayan transform. The Mayan transform. And so essentially that. So really, also there's a division or multiplication by the square of this function. So it's not just a conjugation. This corresponds to corresponding to the wave operator box being homogeneous of degree -2. So okay, so what we have is, on the other hand, we have a nice operator with smooth coefficients on globally defined sphere. On the other hand, in open subsets of the sphere, we have operators we care about, which is spectral families of Laplacians and de Sitter wave operators. Okay, and they relate to each other locally by conjugation, essentially, maybe up to some division. And so so given this, it's maybe not surprising, but there's something significant to prove that you can relate the spectral theory and scattering theory for these operators to that of an operator on the sphere. So, so the main point is that the spectral and scattering theory for either one of these two things can be related to this operator, to a family of operators, on the sphere, which is a compact manifold without boundary. I mean, this is the simplest possible thing one can do analysis on. So this just could not be any better. The only downside is that it's not going to be an elliptic operator. So this operator has exactly those features. So the upshot is that these two operators are in some geometrically complete, non-compact spaces. You can compactify them, but they become degenerate in a certain sense. And it's not so easy to do analysis on these. So instead, if you are a Microlocal analyst, you can just work on a compact manifold with a non-elliptic operator, but an operator of the kind that you perfectly nicely understand, and do everything with that. And that implies everything you ever wanted to do for both of them at the same time on top of it. So like, what could be better than this? You sort of do two at once. So maybe in the last few minutes, let me say a bit more about what this looks like to make it a bit more concrete. So I said a bit, I think the first lecture, about conformally compact spaces. So of course, you don't want to do it just for these spaces. That's supposed to be an example. So these were spaces. So this was, you have, well, I guess I keep calling this M. So let's call it X now. So X is my, my manifolded boundary with boundary. And then so X is the interior. And then I have a little x as a defining function. And then what I want is a metric G, which is supposed to look like G hat over x squared, where G hat is a metric on, in an honest sense, on this compact. So let's make this compact. It doesn't matter until we do our honest analysis, but then it does matter. So G hat is a metric on X, and then you get to decide what sort of metric it is. So for example, it could be a Riemannian. So this would be asymptotically hyperbolic spaces. You need one extra condition, but you could have, if it's not Riemannian, so we could have it Lorentzian. By the way, I didn't say this, but just as an aside, this framework that I described, so this works very nicely, for example, for ultra-hyperbolic equations. So Cauchy problems are a horrible thing for ultra-hyperbolic equations, but these sort of radial points, whatnot, frameworks are just great. So anyway, but that's not the ultra-hyperbolic. So G hat Lorentzian, then what you get to decide is you get to decide on the type of the boundary. So then the question is if the boundary, so this could be space-like for G hat. So this would be asymptotically de Sitter. Or it could be time-like. Well, of course, it could be intermediate or mixed or whatever, and light-like things added up. So it could be time-like for G hat. And this would be an anti-de Sitter space. So you really want one more condition, which is that so the asymptotically constant sectional curvature which just amounts to saying something like that dx has a constant length relative to G hat. So equals to, let's say, squared. So the usual thing, this is equal to plus minus 1, whichever sign it's supposed to have. So this is just really fixing the asymptotic curvature. So it's not like a variable asymptotic hyperbolic metric. So that's this is the sort of more general setting. And then quickly say something about how this relates, and then finish this next time. So so to be concrete, so e.g., and you can always arrange this by, and so this can be arranged near the boundary. You can always arrange sort of a local product type behavior under this assumption. G hat looks like dx squared. So this would be, say, the asymptotic hyperbolic setting plus some h of xy dy, or so this is asymptotic hyperbolic. And the de Sitter version would be that G hat is dx squared minus h xy dy. And so here h is Riemannian, and here h is again Riemannian, so on the boundary. So positive definite on the boundary. Okay, so so this always can be arranged. Now it turns out that there's one more thing that makes a difference here. So these metrics are called even. If h is an even function of x. So this actually is well defined, and so this is, you can write this down in a better way, but I'm not going to do it. So this is due to Guillermo. Okay, so in other words, h is h of x squared. So this is a bad notation, but I'm just going to say this. Okay, and so so if you have this, then you can write down the Laplacian of your metric G in the hyperbolic case, or for the elliptic problem, i.e. in hyperbolic space, or for the hyperbolic problem, i.e. in the Lorentzian space, in de Sitter space. And so these roughly behave like, quote unquote, roughly. These are going to behave roughly like x dx. So the actual metric is divided by x squared, and here the dual metric is what enters. So it's going to look like x dx squared. So certainly these are the highest order terms, plus Laplacian y. H. But this looks like x dx squared. X squared minus x squared Laplacian h. So that's what they look like to leading order. Now, okay, so suppose someone gives you an operator like this, and then you are given the task to analyze its spectral family. So you want to analyze something like Laplacian minus n minus 1 over 2 squared. This is just the sort of a convenient normalization for these, because it corresponds to the bottom of the continuous spectrum. Well, anyway, so you want to analyze something like this. So this is the resolvent family. And so here, im sigma is, say, positive first. So that corresponds to this. Supposed to be the honest L2 inverse. So this is the so let me point out that this is a complete metric. So this is essentially self-adjoint on CC infinity by Chernov's theorem. I mean, there are much more basic proofs of that too. But anyway, so you can ask how this behaves, and so you would like to analyze this. So in order to just say a word about what is the relationship of this to this Minkowski picture, so what you can do is that we can conjugate. So it's really going to be the same sort of statement. One can conjugate. So this is really doing exactly what I did in Minkowski space, except that now I don't have Minkowski space to back me up. So conjugate the spectral family, and I can do the same thing with the de Sitter. So this by essentially something like x to the something like I sigma. Maybe it's minus I sigma, I can't remember. But anyway, something like this. Conjugate by this and divide by x squared with the following result. And then, if we let, this is bad notation, but you know, I used it once and then I'm stuck with it. Then if we let mu equals x squared, so this is where the evenness comes in, then the coefficients of the operator continue smoothly and non-degenerately. So here x was positive, and so mu is positive. I mean, going down to 0, but we're going down to now mu negative. So notice that mu negative, this would correspond to, if I really thought of x seriously, which I'm not going to do, but if I really did think of this seriously, this would correspond to x imaginary. So what you're doing, in terms of what physicists would say, is that you're doing a Wick rotation. But that's, so that doesn't really make sense in this setting. But what we are doing here honestly makes sense. And just to give you an idea what this looks like, let me just write down the metric, or the dual metric. So there was here's the Laplacian modulo irrelevant terms. So this looked like x dx squared plus x squared Laplacian h, right? So this conjugation does nothing. So conjugation is irrelevant for just the, so this is really the principal terms, second order terms. So the conjugation by x to whatever power does not change the second order term. So I don't have to worry about them. That's very nice. So of course, it's crucial for dealing with the lower order terms, because otherwise they will not extend smoothly. Okay, so I don't have to worry with the conjugation. So all I want to do is I want to divide by x squared. And so here, notice that, so this, or I might as well write it, because I don't care about lower order terms, I can just write it as x squared dx squared plus x squared maybe I, no, actually it's fine, sorry. I'm just going to leave it like this. This is fine. So, so what I want to do, remember I want to let mu is equal to x squared. And what this means is that then x dx becomes, I think, if I do this right, 2 mu d mu. So my operator, Laplacian g, again, this is really dual metric that I'm writing down because I'm ignoring lower order terms. This is really just 4 times mu d mu squared plus mu times Laplacian h. And so now if you divide by mu, so this is a mu in front, this is a mu in front, I can just divide from the left. And what you get is, is just 4 d mu, mu d mu, plus Laplacian h. You get an operator like this. OK, so notice here what happens. So remember, this is a 1 over I in it. This is a 1 over I in it. So this is elliptic in mu positive, but it's actually hyperbolic in mu negative. And mu is the time variable here. And what will happen is that it actually has radial points at mu equals 0, really at the corner bundle of mu equals 0. So that's what corresponds, in the Minkowski's picture, that's what corresponds to the boundary of the light cone at infinity. Okay, so I will just start from here tomorrow. So I will write down also the lower order terms so that to make it even clearer what's happening. But basically, the upshot is that we have this picture. So here's my mu. So here's mu positive. So I have this hyperbolic space here. In mu negative, in fact, if you do the same calculation, you see that this is really what corresponds to the de Sitter space. Here's mu equals 0, where I will have some radial points. So the equation sort of changes type. And then, explicitly, such an expression sort of glued the two together, in some sense, wick rotating hyperbolic space when you go to the other side. This is like a wick rotation in terms of the original boundary defining function x. But if you work it in terms of x squared, then all that happened is that you went through the boundary. So nothing happened. Okay, so everything just extended smoothly. And this is sort of non-degenerate. It's just really radial points that it does. So I talk about this more tomorrow.